Welcome back everyone. In this lecture I will actually give proof of Möbius inversion formula. So, let us start with stating the result. So, recall that we are working with the finite poset P with the partial order less than or equal to. So, this is the finite poset. So, now what we do, we actually the Möbius inversion formula that actually relates two functions that are defined on this finite poset P. So, to be like more accessible, what we will do, we will just work with complex field. Okay. So, our field will be always complex numbers. Actually, one can replace this complex numbers by any commutative ring, that is not a big problem. So, we actually going to look at functions that are defined on P which takes complex values. Okay. So, complex valued functions from P. So, what is Möbius inversion actually asserts? So, we take the finite poset P less than or equal and then two functions, let us say f and g defined from P to C, complex valued functions from P. Suppose that g and f are related by the following formula. Okay. Suppose that g of y is given by summation f of x, where x is less than or equal to y for all y in P. Okay. If this is true, then what we can do, we can actually write f in terms of g using Möbius inversion. So, using the Möbius function. So, we can write f of y in terms of g. So, we want to write summation g of x, but with some coefficients which are given exactly by the Möbius function mu, where x and y runs over x less than or equal to y, and this is true for all y in P. So, this is what called Möbius inversion. Okay. If g is defined using f, then f is defined using g with the coefficients coming from mu. Okay. So, this is the version 1 and we also have the version 2. So, which is the converse part. Maybe one can write it as if and only if, not a problem. So, conversely, so if we take f of y, which is defined using the second equation, summation mu of x y g of x, x less than or equal to y for all y in P. So, then what one can do, again one can use the inversion. Now, you can write g of y as sum of f of x, where x less than or equal to y, the sum varies over that, and this is true for all y in P. Okay. So, basically if g is sum of f of x, x less than or equal to y, so then f can be rewritten in terms of g and vice versa. So, that is what Möbius inversion guarantees. Okay, let us prove this. So, this is actually very much closely related with how one can actually write a vector in terms of, okay, by applying the linear transformation A, and then how to kind of invert and then write the resulted vector in terms of the original vector that we started with. So, what I meant, like let us say we have the equation like A x bar equal to y bar. So, if A is invertible, okay, so then this equation can be rewritten as follows. So, you can write x bar in terms of y bar. Okay. If y bar is can be written as linear combination of x, and the linear combinations comes from the matrix A which is invertible, then one can rewrite x in terms of linear combination of y. So, that is what the basic linear algebra tells. So, that is what we are actually going to do here. So, the way we wrote g as sum of f, that tells you that the zeta function is indeed involved. So, now by inverting the zeta, we will actually get the Mobius function there. Okay, let us do that properly. So, as before, what we will do, we will fix a linear extension of the partial order that we have. Okay. So, let us write P as x1 etc. xn such that xi less than or equal to xj implies I less than or equal to j. So, this is the linear extension that we are fixing. So, now what we will do, we will just rewrite the formula, okay, that written for g. So, recall g of y is given by summation f of x, x less than or equal to y. So, that is how we defined g. Okay, for any given y, we have this equation. So, this means if I write this in terms of xi xj, so write x equal to xi and y equal to xj. So, then what we have is g of xj is given by summation f of xi, xi less than or equal to xj. So, this is what it says. So, now we can actually just use the zeta function. So, the zeta function, recall the zeta function of xi xj, okay, maybe I will use some other notation, XOR XS, this is exactly 1 if XOR less than or equal to XS, 0 otherwise. Okay, this tells us that the same equation, this can be rewritten as follows. So, whenever we see xi less than or equal to xj, this we have 1 times f of xi, otherwise we have 0 times f of xi. So, that means this g of xj, you can write it as summation this zeta of xi. So, whenever xi less than or equal to xj, we see this thing. So, xi is varying. So, you have xi xj f of xi, where xi now runs over all the entries. So, maybe we can just simply write it as I ranging from 1 to n. Okay. So, this is because this term is going to be exactly 1 if xi less than or equal to xj, 0 otherwise. Okay. So, that is what the original equation in the proportion tells us. So, now this is something we can rewrite in terms of the matrix language. If you use the matrix language, you can see that we have this f bar, which is given by let us say f of x1 etc. f of xn. Similarly, we have this g bar, which is given by g of x1 etc. g of xn. So, now the equation which we had before, g of xj, which is given by summation that z ij f of xi I ranging from 1 to n. So, this if you think about it, this is just multiplying by the matrix z with the vector f bar. So, you take this z and then you just multiply by this f bar, then what you get is exactly this g bar. Okay. So, yeah. Okay, let us actually try to do this. So, one should be little bit careful. So, if I am looking at the ith row, so the ith row entry will be z I1 etc. z In. So, this is my the matrix z, and then here I have this f bar f of x1 etc. f of xn, which is fixed. Okay. So, if I take this ith row and then multiply by this column. So, that is what I am doing here. So, if I look at this is exactly okay, sorry, this is actually I is running. So, that is why I said we should be little bit careful. So, indeed what we are doing, we are indeed multiplying by the transpose. So, this is the transpose here. So, what is the transpose? So, let us quickly recall the transpose. Suppose A is the matrix which is given by Aij, then the A transpose is the matrix whose ijth entries are given by Aji. Okay. So, in terms of the matrix, what you do, if A is given by this A11 etc. A1n, A21 etc. A2n and so on, AN1 etc. ANN. So, then the A transpose is given by take this column and then put it as a row here and so on. This column we put it here. Okay. So, that means what we are doing, we are simply writing this as A11, A21 etc. AN1 and so on, and then here it becomes A1n, A2n etc. ANN. So, this is the transpose of the matrix. So, now if we take the transpose of Z, what we get, the Z transpose. So, the ith column, you can see that this is going to be exactly A. So, let us read it from here. So, what will be the ith column? So, the first column becomes the first column becomes the first row of A transpose. That means, the ith column here becomes the ith row here, the ith row here. Okay. So, that means, this is exactly A1i, A2i etc. ANI. Okay. This is my ith row of G transpose. So, now if we take this thing and then multiply with f bar, which is f of x1 etc. f of xn. So, then you can see that you get exactly A1i f of x1 plus etc. plus ANI f of xn. So, which is exactly given here in this formula. Okay. Because this I is actually varying, this j is fixed. Okay. Okay. So, I should take the jth row instead of ith row. Okay, that is fine. So, you just change this to j. So, this is j, j and j. Because I is varying, j is fixed. Okay, let us rewrite. Now, if we rewrite, then what we are getting exactly, the Z transpose f bar is exactly given by G bar. Okay, this is the equation that we are getting. Okay, that is what encoded in this equation. So, now we have the relation that m z and z m is exactly the identity. Now, we know this from linear algebra that A B transpose is exactly given by B transpose A transpose. Now, if we use this equation, then it is clear that Z transpose M transpose, which is equal to M transpose Z transpose, which is equal to the identity transpose, which is exactly identity. So, that means the transpose of the Mobius function becomes inverse of the Z transpose. So, now we have this equation Z transpose f bar equal to G bar. Now, by multiplying by m bar on both sides, m transpose on both sides, we get exactly this equation that f bar equal to m transpose G bar. Okay. So, this is what we are getting. So, now we can rewrite this equation. So, if we rewrite this equation, then it is clear that if you fix the jth entry, so from this it is clear that f of x j is exactly going to be summation m I j g of x I, where I runs over from 1 to n. Okay. So, as before, just write down m transpose what it is, and then g bar you just multiply, you get this equation. Now, we know already what is m I j. So, m I j is nothing but mu of x I x j, and mu of x I x j is 0 whenever x I not less than or equal to x j. So, that would tell us that f of x j is exactly equal to summation mu of x I x j, okay, because that is m I j g of x I, and then now we need to vary all those x I which are less than or equal to x j. If it is not the case, then mu of x I x j 0. So, that would tell you this is going to be 0. So, that entry will not contribute. So, then we get this equation. So, now this equation can be rewritten as follows: f of y equal to summation mu of x comma y g of x, x is less than or equal to y. So, this is what we have it in the Mobius inversion formula. So, if we go back to the Mobius inversion formula, basically that is what we have. So, now conversely we can again rewrite the second equation. So, again it is that equation actually tells it is multiplied by m transpose. So, now if you just use Z transpose, then you get back your G. So, let us just quickly go through. So, if we start with this equation that f of y equal to summation mu of x comma y g of x, x less than or equal to y, and if you again do the substitution, then this is exactly says that f bar is given by m transpose g bar like before, and that would imply Z transpose f bar is exactly Z transpose m transpose g bar, which is g bar. So, that means we have Z transpose f bar equal to g bar. So, basically the theorem can be rewritten as follows: we have Z transpose f bar equal to g bar if and only if f bar equal to m transpose g bar. So, that is all the Mobius inversion formula says in terms of the matrix. Okay. Even though it looks like a very simple formula that uses basic linear algebra, it is a very powerful tool in combinatorics and basic number theory, because any number theory functions which you can write it like g in terms of f, then you can use this Mobius inversion to rewrite f in terms of g, which is very often useful, because sometimes the function g can be computable, and using Mobius inversion you can write down a formula for f in terms of g which can be computed. One drawback is that the Mobius inversion of course uses the alternating signs, okay, that actually kind of that does not give us any non-negativity formula. So, even though you write f in terms of g, which is mostly computable function, we may not be able to get very nice non-negativity formula. So, it will be always some alternating sum. So, that is the biggest drawback in using the Mobius inversion, but still it is very useful, because most of the time g will be very much computable. So, f you can actually get it from g, that is already big achievement. Okay. So, let us see some basic examples and then try to compute the Mobius function, and which actually tells immediately how the Mobius inversion works. Okay. So, I am going to actually do only 1 or 2 examples comes from set theory, and some more examples for example some number theoretic functions, where you can use Mobius inversion or number theoretic Mobius inversion and so on. That will be discussed in the upcoming sections in that are part of number theory. So, again there will be some applications of Mobius inversion that we will see later in graph theory, okay, when we talk about coloring, chromatic polynomials and so on. But to be like more accessible, we will only talk about very basic Mobius inversion like so let us start with something like this standard totally ordered set which is 1 to n. Okay. So, let us take P to be 1 less than 2 less than n. So, we take the standard total order on 1 to n, okay, and this is obviously a partial order. And now one can ask what is the Mobius inversion and what is the Mobius function. So, the Mobius function which we want to compute, we need to compute what is mu of I comma j, what it is. Okay. Already we know some information, mu of I comma I is exactly 1 and mu of I comma j is going to be 0 if I is greater than j. So, this much we know. So, we need to only compute mu of I comma j when I is less than j. Okay. Indeed, we are going to prove that this is exactly minus 1 and yeah, it will take only 1 0 or minus 1. So, let me just copy paste. So, whenever I is I plus 1, it takes the value minus 1, otherwise it is 0. So, it is 0 when I is less than j, which is so let me put it this way, when I plus 1 less than j and it is minus 1 if j is exactly I plus 1. Okay. So, this is same as saying that j minus I is stays away, like it's the distance between I and j is at least 2. Okay, this is the Mobius function in this case, and let us actually try to prove. This is again like follows immediately from the defining relations of Mobius function. So, let us write down the defining relation. So, you have summation mu of I comma k, where I less than or equal to k less than or equal to j. So, this is given by like now we will just take I is not equal to j. So, this is going to be 0. Okay. So, this is what we have. So, now using this like we can rewrite this as so let's come from the top. Okay. So, if j is I plus 1, then we have mu of I plus mu of I plus 1, which is 0. So, this implies that mu of I plus 1 is exactly minus 1, because mu of I is 1. Okay. So, this is done. So, this case is done. So, that is what written here. Now, assume that j is strictly greater than I plus 1. So, then in this case what we have? We have mu of I plus mu of I plus 1 plus mu of I plus 2 plus etcetera plus mu of I comma j, this is going to be 0. So, now note that this is 1 and this is minus 1. So, they just get cancelled out. So, that gives us this equation that mu of I plus 2 plus etcetera plus mu of I comma j is 0. So, now by induction you can just induct it on j minus I. Okay. So, induction on j minus I tells us that. So, all these terms are 0, each individual terms are 0. Okay. So, implies that mu of I comma j is 0, because mu of I comma j will be minus of all these terms mu of I comma I plus 2 plus etcetera mu of I comma j minus 1. But all those terms will have this the difference j minus I more than like sorry less than that j minus I. So, that would tell you that this is 0. For example, if you want I plus 2, so then so if j is I plus 2, you can see from this equation this part will not be there. So, that will imply 1 minus 1 plus mu of I plus 2 is 0. So, that implies that this is 0. Okay. So, like that by induction you can just prove that all these terms are 0. So, that implies this is 0. So, this tells what is the Mobius function in this case. So, now if you have a function which is let us say g of j, which is given by summation f of I less than or equal to j, then using the Mobius inversion you can write f of j in terms of summation mu of I comma j g of I, where I will vary over from I less than or equal to j. Now, mu of I plus 1 is the only thing that survives and mu of I survives. So, mu of I is 1, which gives g of I, and then plus you have I plus 1. Okay. So, that tells if sorry I is what varying, if I equal to j, if I equal to j you get mu j which is 1, and then when I is j minus 1, then you get exactly minus 1. So, this is mu of j comma j, this is mu of j minus 1 j, which gives us this equation. So, this is exactly g of j minus g of j minus 1. So, that means we have this standard finite difference formula. So, which says f of j is given by g of j minus g of j minus 1, which is very clear from this equation. Okay. If you take g of j minus g of j minus 1, we get exactly f of j. Okay. This completely fits in the general theory. So, similarly like one can do even the inclusion exclusion as an application of this Mobius inversion. So, let us look at that. Okay. So, this is example 2. So, we take E to be a finite set, and then we look at this 2 power E, which is the power set of E, okay, all the set of all subsets of E, which is my Poset P. The inclusion, set inclusion is my partial order. So, then one can verify that if S is contained in T, so then the mu of S comma T is given by exactly minus 1 power the cardinality of T minus the cardinality of S. Okay. Of course, mu of SS is going to be 1 and mu of S comma T is 0 if S is not contained in T. Okay. Mu of SS is 0 and mu of S comma T is 0 if S is not contained in T. So, these are all already part of the definition. So, we are not going to write that. So, let us verify this is indeed the case. So, recall that how the Mobius inversion defined. So, let this S is contained in T, then we have this equation summation mu of S comma u, where u will run over in the interval bracket S t. So, that means u contains S and contained in T, and this we know is exactly given by 0. Okay. So, that is what we need to verify. So, the defining relation which actually already tells this is the case in these two particular scenario, and when S is contained in T, we need to verify what it is. The defining relation will tell you this summation should be 0. Okay. So, to verify that we will just compute what it is. So, by replacing this by minus 1 power cardinality of T minus cardinality of S. So, I am simply directly verifying this summation is exactly 0. This is my claim. Okay. So, how this is actually done? So, recall this S is somewhere here and then T is somewhere here, this is S, this is my T, and there is this S minus T that is outside. So, now if I am actually looking at all possible U which contains S, then this U will take some elements from this complement. So, U will be S union T minus S intersection U. Okay, this is how the U will be formed, and this will have whatever number of elements that we are interested in, let us say k elements. Okay. So, now okay, this is SU. So, this is supposed to be U. Okay. So, now let us compute this. We want to compute summation minus 1 power the cardinality of U minus cardinality of S, where U comes from this S and T. Now, if I fix the cardinality of U minus cardinality of S to be k, which is exactly this part, okay, then how many such k elements set that we can actually form? So, these k elements chosen from T difference S, but let us say the T difference S has the cardinality M. If they are chosen from these M elements, how many choices are there? Exactly M choose k choices are there. So, that means we have M choose k choices for this U such that the cardinality of U minus cardinality of S is exactly k. Okay. So, that means this summation is going to be the summation k now runs over from 0 to M, and then if I fix this to be k, then this is minus 1 power k M choose k. This is what we have, but we already know that this summation is actually 0, okay, because this is exactly 1 minus 1 power M, which is 0. So, that tells you that this function that we have written here, so that indeed satisfies the defining relation of the Mobius function. So, that is good enough to tell that this is indeed our Mobius function. So, now if we use the inversion, what it says, if you write g of t equal to summation f of s containing t, then that would imply actually if and only if f of t you can write it as summation g of s, where s is contained in t with the Mobius coefficient, which is minus 1 power the cardinality of t minus cardinality of s. So, this is the most general form of inclusion exclusion principle, and many textbooks, for example, give this as immediate application of inclusion exclusion. Now, by choosing some very particular choice of this g, one will be able to recover the classical inclusion exclusion principle. For example, we can take in this scenario, let us say x is a set and then a1 etc. some a n given to be subsets of x. Okay, this is let us say finite set, everything is finite. So, now for given s in n, define g of s to be this intersection of a I in s, the cardinality of that. Okay. So, with the convention that g of mt being the cardinality of x. Okay. So, for given s in this bracket n, if we define this, so and then if we take f of s, to be the number of elements of x. So, this is exactly the number of elements of x that belong to exactly the sets A I. Okay. So, this is very important, exactly the sets A I where I in S. So, then it is clear that we have the relation g of s is exactly given by summation f of t, t contains s. Okay. So, this is immediate. I will leave it to you to verify this. This is not very hard thing to verify. So, now using the Möbius inversion, you can see that f of s, you can write it as summation minus 1 power the cardinality of t minus cardinality of s g of t, where t contains s. So, now by applying for s equal to m t, what we get exactly f of m t equal to summation minus 1 power the cardinality of t g of t, t contains in 1 to n. But what is f of m t? F of m t consisting of all the elements or counts the element that belong to none of the sets A I. So, that means it is exactly the cardinality of the complement. So, f of m t is exactly the cardinality of x difference union A I range from 1 to n. So, which is given by the summation minus 1 power the cardinality of t, the g of t. Recall the g of t is exactly given by the intersection of A I in t, where this t now comes from this 1 to n. Okay. So, this is our classical inclusion exclusion that we have actually already seen. And if you take only the union of A I, and we know how to actually write down that as well. So, the union of A I range from 1 to n, the cardinality of this is exactly the cardinality of x difference this, which is given by the summation minus 1 power the cardinality of t plus 1 intersection of A I range from I is coming from t, the cardinality of this, where t is non-empty, runs over from 1 to n. Okay. So, these are all the formulas which we already seen. Okay. Okay. So, I will stop here. So, this actually kind of completes everything about Möbius inversion. So, in the next class we will actually start with basic graph theory. So, in basic graph theory, what I am going to do, we will actually define basic notion of graphs and the matrices associated with the graph and characterization of trees and some basic notion like Eulerian cycle, tours and so on, we will see. And later we will move on to like defining some polynomials associated with graphs like matching polynomial and then chromatic polynomial and so on. So, this introduction, like brief introduction of graph theory, we have included in this course, so that you get some familiarity with the graph theory. Of course, we will not be able to do everything that one does in the first course of graph theory. This is just a very simple introduction to the graph theory, so that you will be very comfortable whenever you see the notion of graphs in the future. Okay, I will stop here. So, we will start with the graph theory in the next class. Thank you.